I'm Wang from Xorbits AI. Thank you for joining me today, and I'm here to talk about our open source project called Xinference, a platform that simplifies working with generative AI. Xinference provide a serving feature for language embedding, re-ranker, and image models. And today we'll focus on large language models. Okay. So I'd like to start with an introduction of large language models, or LLMs for short. These are complex AI models designed to comprehend, generate, and interact with human language. The applications are vast and diverse, touching many aspects of our lives. I'm sure you guys are all familiar with ChatGPT, which is one of the most popular LLM application. In fact, I use the ChatGPT to help prepare this very speech script, and it's very useful. Well, ChatGPT is great. It has some limitations. For instance, you cannot use ChatGPT to summarize sensitive documents, and that's where open source models come into play. So let's talk about open source large language models. There are a lot of them. Open source models like Llama offer several key advantages over closed source models like GPT-4. They may not be that powerful, but firstly, they can provide better data privacy and security. Since you have control over the data and infrastructure, it's much easier to ensure the sensitive information is handled securely. And secondly, there's a benefit of customization. Open source LLMs can be further fine-tuned to finish specific needs and applications with your private data. And thirdly, they are cost efficient, especially when compared to OpenAI's API. You can save a lot from prompting engineering and experiments. So open source LLMs are awesome, but there are still challenges. For example, choosing the right model from a vast array of options can be daunting. And you also need to figure out the correct prompt format, which is critical to interact with an LLM. And it could be different from model to model. And serving efficiency is another critical aspect, as deploying these models at scale can be resource intensive. Xinference is designed to simplify the process. Okay. Now I'd like to officially introduce Xinference. So the platform is designed with ease of use at its core. We offer a user-friendly interface and have simplified the process to ensure that even those who are new to AI can navigate and utilize our tools effectively. One of the standout features of Xinference is its cross-hardware platform. Whether you are using GPUs from NVIDIA, AMD, or you are using Apple Silicons or other accelerators, Xinference is designed to work seamlessly. Xinference is also good at performance and scalability. It's built to handle high-demand scenarios efficiently, and ensuring that your needs grow, the platform could scale with you and maintain the performance without compromise. Furthermore, we have integrated with popular third-party libraries, including Defy, LangChain, Llama Index, and others. This integration can help developers to build an application based on large language models much more faster. So let's have a look at how to use Xinference. Xinference provides a flexible API. It has its own Python client, but since OpenAI's API is a de facto standard in the industry, we also provide an OpenAI compatible API so that users can use Xinference with OpenAI's Python client, which is an enhancement to user experience. Xinference also provide a web UI to simplify the management of AI models. It's user-friendly and makes managing models straightforward and efficient. As you can see, you can launch a SOTA model with a single click, and you can view the running models, and you can register a custom model with Xinference. And once you choose a model, Xinference will download the model and launch a model instance for you. You can then chat with the model or let the model generate text on the web UI. Or you can use a third-party LLM ops to do prompt engineering and others. Okay, so let's see how Xinference simplifies the creation of prompts. This is not about prompt engineering. This is about how to interact with the model correctly. It's a critical part of interacting with LLMs. So firstly, the prompt templates format the user's input to align with the model's training data. This ensures that the model interprets and responds to the prompt as expected. It's a very important step as the models are sensitive to how inputs are structured. So for example, a simple user input like "hi there" in Xinference, it is not just passed directly to the model. It is extended to a comprehensive prompt in the following. It includes a system prompt like "you are a helpful, respectful, and honest assistant." And it also comes with the special tokens in front of and in the end of each instruction. And when you want an LLM to use external tools or invoke an external functions, like let's say a search engine API, you need to integrate a description of the tools into the system prompt, like what does the API looks like and what are the parameters. So for different models, the format of the function call description is different. It's kind of hard for users to learn about everything about every model, and Xinference handles this complexity here. Okay, so let's talk about the cross-platform support. Xinference can be deployed on different hardware platforms, including NVIDIA and AMD GPU, and Apple Silicon, and CPUs. This is achieved by accommodating various engines to suit different models and hardware setups. So as you can see, we have supported VLLM, Tensor LLM for NVIDIA platform. They are closely integrated with NVIDIA's accelerators and they can deliver great throughput. And we also support transformers by Hugging Face. It is known for its extensive compatibility, and it supports almost all the model architectures, and they can run on almost any accelerator. We also support GGML-based engines like Gamma CPP. It is optimized for edge computing, and it runs pretty well on CPUs, and can also benefit from a wide range of accelerators. So as you can see, there are many hardware platforms, and sometimes it's hard for users to figure out the right engine to use. And Xinference will choose appropriate engine intelligently according to your hardware platform, which greatly simplifies the model deployment. Okay. And let's talk about the GPU memory management. So everyone knows that GPU is really limited right now. So it is very important to use GPU memory efficiently. During inference, GPU memory usage is actually divided into three main parts: the model weights, the activation, and the KV cache. So generally, the KV cache it's a technology to accelerate inference, and it often occupies the most GPU memory. And generally, the more GPU memory allocated to KV cache, the higher throughput you can achieve. But it's hard for users to do the math and calculate, like given a desired throughput, how much GPU memory they should allocate to KV cache, right? And Xinference helps in determining the optimal amount of GPU memory that for KV cache based on the desired throughput provided by users. Xinference also ensures that there's no risk of running out of memory during operations, which greatly improves stability. The issue actually is that when the sequence gets longer, the amount of GPU memory for KV cache should increases. So if you are using transformers and without any like GPU memory management, it's very likely that when you are working with a long sequence, there will be an out of memory error, and you will not get what you want. So this careful management of GPU memory is really helpful when running multiple models on the same GPU. For instance, for an RAG application, you will need three models. One of them is a large language model, and you will also need an embedding model and a re-ranker model. So if you want to run the three models on a single CPU, you have to figure out the GPU memory allocation so that during the inference there won't be an out of memory error. And this is handled by Xinference. So I'd like to talk about the performance and scalability of Xinference. Xinference also leverages parallel decoding algorithms to achieve better performance. So the idea of parallel decoding is instead of like the autoregressive algorithm, which generates one token at each iteration. Parallel decoding algorithms try to generate multiple tokens at each iteration. Speculative decoding is one of the most popular parallel decoding algorithms. Other parallel decoding algorithms, including look-ahead attention and Medusa. And the core of this speculative decoding algorithm is to use a smaller, quicker draft model to generate several tokens in advance. Since the weight of smaller model is much smaller and the amount of GPU memory required for KV cache is smaller, it can achieve better latency and better throughput. So when you have several tokens generated from the draft model, you can invoke the larger model to validate the result. This is done by parallel. You can actually get a score of possibility of each token at one iteration of the larger model. And once you get a score, you can determine whether this token is good or not. If it is good, I mean it's higher than a certain threshold, you can accept a token. And if it's not, you can discard the token and the token followed the following tokens. So if the draft has a high acceptance rate, it can lead to a great speeding up. The effectiveness of this algorithm depends on two factors: the size difference between the models, the larger the better, and the similarity of the logits produced by both models. Using a 7 billion parameter model as a draft model can speed up inference in a 34 billion parameter target model by about 25%. And impressively, a draft model of 7 billion parameter can accelerate a 30 billion parameter model by up to 100%. Here's a demo of Llama 30 billion. And as you can see, on the left side is a speculative decoding instance, and on the right side is a regular instance. And the speculative one is much faster than the regular one. And it's really simple to use speculative decoding in Xinference. You just need to specify the draft and target model, and then you launch the LLM. Once set up, the system treats it as a regular model, handling the complexities of speculative decoding internally. This means a user can enjoy the benefits of a faster model inference without any additional complexity in their workflow. And for the last part, I'd like to talk about the scalability of Xinference. So as the demand increases, Xinference can scale out accordingly, ensuring that throughput increases and latency decreases in a linear fashion, maintaining performance and speed. So to illustrate this, let's look at some experimental data. We conducted tests using NVIDIA RTX 3090 graphic cards. The results were quite remarkable. When we compare the performance on a single card to that on a dual card setup, the throughput nearly doubled. This improvement in throughput is significant as it demonstrates the platform's ability to handle higher volumes of data processing without bottlenecks. Equally important is the reduction in latency. The dual card setup decreased latency by about 80% compared to a single card. This reduction means that you can add more resources to Xinference. The time taken to process each unit of data decreases substantially, making the system faster and more responsive. Okay. Thank you all for your time and attention today.